Exactly 2 years ago, in March 2020, Germany started their first COVID lockdown. And as we all know, that wasn't the last lockdown. The virus kicked off a global pandemic, which forced a global change in lifestyle. The coronavirus is an infectious disease that causes symptoms such as fever, coughing, and respiratory narrowness. Daily infections, daily vaccinations, and daily deaths yield a huge mass of data that hopefully facilitates the understanding of this virus. However, these dashboards are sometimes overwhelming and hard to interpret. As students of the class Clinical Application for Computational Medicine by Professor Martin Daumer, we present a first version of a web-based application for the simulation of the corona spread probability. As a motivation for our software, we will look at an example now. Here we have Steven. Steven is an ordinary man who works at a factory, and he is eager to follow the news and politics. But since the coronavirus, he feels overwhelmed. He is afraid of being misinformed or influenced, and he has a lot of doubt. He wishes to have some kind of a simulation that helps him to understand and visualize the effects of restrictions. So in this project we came up with a COVID-19 simulation tool that allows the user to play around with different parameters. Before going into our work, we just want to highlight the state of the art for this kind of simulation. So why is it important that mathematicians and software engineers work on something like a corona simulation? Compared to other people like businessmen, politicians, or even school teachers, mathematicians or scientists are unbiased and they work fact-based in order to predict the future. The only goal and the only interest they will have is that they make a realistic and authentic simulation. There's such kind of a group of scientists from the University of Göttingen who work at the Max Planck Institute, and they came up with mathematical models that can predict the coronavirus behavior over time. The team of Jonas Dening and especially Miss Dr. Viola Priesemann, who is a public speaker and also a political advisor for the COVID-19, benefited the society a lot in the past 2 years. Reading the work of this team really helped us to get along in our project. In the next part, I want to talk about the compartmental modes in epidemiology. So, depending on the virus, different mathematical models exist. For example, the SIS model that, for example, exists for a common cold or influenza, which just means that either you are susceptible or you get infected. And after being affected, you don't really get recovered. You don't really have a recovered status that protects you from being affected again. So, as a result, you become susceptible again. However, this is different for the SIRD model. This model is more realistic in the case of the COVID-19 virus. In this case, we have 4 parameters: susceptible population, I for the infected, R for recovered, and D for the deceased who died. So how is the interconnection between these 4 parameters? So as we see, there are 3 factors in this constellation. Beta is the infection rate, gamma represents the recovery rate, and mu represents the mortality rate. So due to a certain infection rate, the susceptible people become infected, and from there on, depending on the rate, this person either recovers or it becomes deceased. Obviously, in mathematical models we have some kind of equations. In this case we have differential equations. So before jumping to the demo of our software, let's talk about some visual aspects. Here is a person like Steven. So what we do here is that dots are representing persons. These dots move around in that simulation, and we tried to find a realistic movement function and decided to use the Levi flight.
Enough now with the theoretical presentation, and let's load up the page. This tool was implemented using JavaScript libraries Py.js, Mat.js and Chart.js. There is a parameter panel on the left, as you can see. The simulation is displayed on the canvas on the right. The first 4 parameters are set for the entire simulation run. You can also set them by checking the box Use current RKI data, which pulls the current COVID numbers of Germany from an API. The bottom 3 parameters can be changed while the simulation is running. Well, there are normal individuals in black, infectious people in red, recovered or immune are in green, and diseased people will appear white. They move according to the Levi flag. Pretty cool, or? The simulation constantly updates the SIRD model and uses the set parameters as well as the state probabilities to update an individual's health every day, which is 3 seconds in this simulation. The number of the simulation are then graphed in the chart below. You can invoke 3 scenarios. The first one is an event that draws a certain percentage of individuals to it and simulates a mass event which skyrockets the number of infectious people. Well, for example, you can take a football stadium where people are gathering together. The second one is self-isolation of the infected, which stops the movement of those. The last one is the extreme case of a lockdown, which stops the entire movement of all individuals. You can observe the chart below to see how these scenarios strategically impact the numbers. Please note, an important disclaimer has to be made here now. This tool is an oversimplification of the current corona situation, and it has to be used with caution. However, please feel free to visit the website at GitHub and play around.
Now we hope that Stephen has a more comprehensive overview of the corona situation, and thank you guys for your attention.